This lecture is intended to help you understand how to use some of the tools we've talked about this semester to assess management scenarios. All of the management scenarios or all of the management recommendations that you're making are intended to achieve landowner objectives for any particular stand that you're making that prescription for. But we often have different ideas for what prescriptions we might apply to achieve management objectives. And it's not always obvious how we choose among those alternatives. So this lecture is intended to really focus on the tools of cash flow analysis and growth and yield modeling and how to pull those together to look at different scenarios and help you make decisions between alternatives. So really the question is, how do you know whether your proposed management plan or scenario is the best possible one? And that's sort of a straw person question because you really can't. There really is no quote unquote best alternative. And that's because there are almost infinite possibilities. There's different timings of treatments, different treatments to choose, different rotation ages, different species to plant, and so on. So really, there are sort of any number of possible futures and any number of management options that would work. So we can't choose a best one. However, we do need to choose a plan that is reasonably efficient in achieving management objectives. And in this case, we really mean efficient in terms of economics and in terms of time. Are you recommending an option that is efficient in terms of dollars spent and how those balance against the revenues produced by your proposed scenario? And does your option achieve those objectives in a reasonable amount of time? So that is really what we're talking about in this lecture. Now, we're not talking about optimization. There are optimization approaches which use different mathematical frameworks to assess scenarios within given constraints and then to choose the optimum, mathematically optimum option. And this is really closer to choosing the quote unquote best option, at least from an economics perspective. Some of the frameworks that are used to do that include linear programming, nonlinear programming, dynamic programming, and you've probably heard those mentioned in other classes. We're really not going to focus on those in this lecture. Those work best for revenue-driven scenarios. And if you are familiar with optimization approaches, you certainly can use them in this project. But in the absence of those types of approaches, we're going to talk about assessing different alternatives, some small number of alternatives, and choosing one that, in a rational sense that makes sense, especially from an economic perspective. So that's really what we're going to be talking about here. The general approach is you look at your compartment, your particular stand that you're trying to make a prescription for, think about the landowner objectives, and then generate several alternatives. Let's say you have a habitat objective, and you think, okay, here's option A, B, and C. These are different sort of silvicultural approaches that I think would make sense. Let's take a look at those. So we'll use models like growth and yield models or data from the literature that help you understand what may play out in terms of those treatments, and then to compare the outcomes of those treatments, especially economically, and compare them to choose whether one particular option achieves the goals sooner or with a better balance of revenues and costs. So that's what we're going to be focusing on here. Just a couple of reminders about cash flow analysis. That's the economic piece of this. Because the scenarios we're looking at, even in short rotation southern forestry, they still play out over decades. And because of the time value of money, because a dollar spent or a dollar of revenue today is worth a different amount of money than a dollar spent or a dollar of revenue 20 years from now. So because of that, we need to use tools that adjust all of those costs and revenues to a common time point. And there's a couple of those that I'm going to remind you about. One of those is net present value calculations. For net present value, we adjust all costs and revenues in any particular year to the present by basically taking that cost or revenue, which would be a future value, and adjusting it to the present by taking that future value. Let's say this is a cost or revenue 10 years from now. We take that cost or revenue and divide it by 1 plus I, where I is the interest or discount rate in a fractional sense. So for instance, a 5% discount rate would be 0.05. And then raise that to n, which is how many years in the future. So in the case that I mentioned, that would be 10 years in the future. And that would adjust that future revenue or cost to the present. So it puts them all on the same footing. Then for a series, so if we're looking at, for instance, a 25-year span of time, you would sum those revenues and sum those costs adjusted to present value and subtract the cost, sum of costs, present value of costs from the present sum of present value of revenues, and that gives you the net present value of your scenario. We can then use that net present value to compare different alternatives, assuming those scenarios occur over the same number of years. So for instance, if we're comparing several scenarios with the same rotation length, if we are comparing different alternatives that occur over different periods of time, so for instance, scenarios with different rotation lengths, we can't use a net present value analysis. And in that case, we might want to use a land expectation value approach. And this essentially takes a scenario and then calculates what the present value of that scenario would be if it is repeated over and over indefinitely into the future. And that basically allows us to adjust out the effect of different rotation lengths, for instance, and compare them on the same footing. So the approach to do that is to calculate the net present value of your scenario like I described on the previous slide. You then take that net present value number and calculate its future value. So we're sort of projecting that to the end of your scenario by taking that net present value, multiplying it by 1 plus I, your interest rate, raised to n, where n is the length of the scenario, for instance, the rotation length. And then you take this value and plug it into this formula where this future value is A. You divide A by this number, 1 plus interest rate raised to n, which is your length of your scenario or your rotation length minus 1. That basically creates the present value of a perpetual series. So it says if we have this, for instance, 30-year rotation scenario and we repeat it indefinitely into the future, what is the present value of that infinite series? And that land expectation value then is a number that we can compare to other scenarios legitimately. So for instance, this is an appropriate tool for determining the best rotation length among different scenarios, for example. Both of these approaches require you to choose an interest rate or a discount rate, and the outcomes of these analyses are very dependent or very sensitive to the interest rate you choose. So it's important that you choose an appropriate interest rate or discount rate, which varies depending on especially what type of landowner you are and perhaps some